Thanks everyone for staying with us for the last session, and thanks the organizer for the great organization. It's great food and great hotel, and also great audience. And I really enjoyed all the previous talks, and I also learned a lot about analysis during this workshop. Could everybody hear me, like in the end? Okay, I'll try. I'll try to keep close to the mic. So my name is Yilei. Right now I work in visa research. So today I'm going to talk mainly about multilinear maps from lattices, about their constructions, attacks, and applications. Also in the previous 2 days, I realized there's a lot of important applications or ingredients in the lattices that many of you asked great questions, but the previous speaker may skip some of them. So I also made some bonus slides that covers a lot of things that are irrelevant about multilinear maps, but they cover some interesting concepts of lattices. So my talk can be stopped at any time, and I can also terminate at any time. The hope is to go through all the interesting stuff, even without finish all the contents about multilinear maps. So hopefully, you can ask questions at any time, and 也可以用中文问问题。So I guess I will just start. Let's try. So what are multilinear maps? So let me start the talk with very simple multilinear maps. So this is the map of Shanghai. I'm also born in Shanghai. So right now we are at this position. So why the map of Shanghai reminds us of multilinear maps? Because all the roads in Shanghai are highly non-linear or multilinear. It's not like a straight lines. So if you take the taxi from the airport to the hotel, so probably you're taking not a straight line because the taxi driver wants to have some fun. And because of the river, actually the roads are built according to the direction of the river. So there's a lot of non-straight lines. And I also heard about, so right now I work in America, and sometimes I watch news from my hometown. I learned that there are a lot of new tourist attractions in Shanghai. For example, the world's largest Starbucks, and the Costco, and Disneyland. These places becomes, somehow the tourist attraction of Shanghai. And all right, so I think you may be tired about these things. So cool. So what are really the multilinear maps in cryptography? So let's start from let's start the multilinear map talking from a really one linear map, which is there's no map, which is simply the discrete log problem in cryptography. Pick your favorite group, say the multiplicative group of the finite field. You are given a generator G and G to the S for some secret S, and the task is to find the S in the exponent. So this is the typical discrete log problem in cryptography. And this problem has found a lot of applications, including non-interactive key exchange and encryption, signatures. Essentially, this is the beginning of modern cryptography. And suppose we have a capability of, say, such a group, where if you take somehow an encoding of S1 and then encoding of S2 from maybe two different or the same source group, and you can map them to the encoding of G to the S1 times S2 in the exponent without knowing S1 and S2 in the clear. So this is now abstracted as the functionality of bilinear map, which is right now we know how to instantiate our elliptic curve from Weil or Tate pairings. So the efficient computation of such a bilinear map was proposed back to '86 by Miller, but it takes a while to find real constructive crypto applications, including identity-based key exchange, three-party non-interactive key exchange, and also identity-based key exchange. So actually, after these three works, there are I think it's fair to say there's tons of work that use this abstraction of bilinear map to build more cryptography capability. So after after its like initial at the beginning of 2000, people realized bilinear map has lots of applications. Even maybe there are only 3 on the screens. Baudet and Silverberg are already thinking about what happens if we generalize bilinear map into multilinear map. So let me roughly describe the goal of a multilinear map. So suppose you have a lot of starting group, say G to a lot of G, maybe they are the same, maybe they are different, and you can somehow encode all the secrets on the exponent. Although in the curve is not really the exponent, but let me just use this notation for now. And by the way, I just want to mention actually computing G to the S1 plus S2 plus all the sum in the exponent is easy. But computing all the product in the exponent turns out to be non-trivial. So if we are able to compute all the product in the exponent without knowing S1, S2, S3, etc. in the clear, this is intuitively what they propose as multilinear maps. So in this paper published in 2003, Baudet and Silverberg, they didn't propose an explicit construction of multilinear map. But they say if you have such a map with intuitive security like harness of solving discrete log or harness of some natural generalization of Diffie-Hellman problem, then you can use this to build potential applications, including having unique signatures, broadcast encryptions, etc. and etc. So, a natural question that we ask is where to find multilinear maps. In the original paper of Baudet and Silverberg, they actually enumerate a lot of efforts of generalizing the Weil and Tate-Perry in the elliptic curve. And in one of the last paragraph of that paper, they say, if an n multilinear map is computable, it's reasonable to expect it to come from geometry, as in the case of Weil and Tate-Perry when n equals to 2. It turns out that in algebraic geometry, like using elliptic curve or hyperelliptic curve or etc., their natural existence result of multilinear structure. It's just we don't know any way of computing them efficiently. Recently, there was a proposal by Huang, I think starting from March last year, is a proposal of constructing trilinear maps from abelian varieties, or maybe in a more concrete word, the minimum algebraic object you can build it is like the Jacobian of hyperelliptic curve of G is 2. So this candidate has been broken and then revisited. So right now it has grown from 11-page paper to maybe a 40-page paper. It still requires further investigation. By the way, I will mention all the open problems during the talk wherever I found them. So the first open question is if you're having a really good math background, this is worth to look at it and understand what's going on. Okay, but today we are in the lattice workshop. And we're going to talk about some existing multilinear map candidates from lattices. So let's see why from lattices. It turns out like it's not following the original proposal of Baudet and Silverberg. Let's see what had happened. So the concept of multilinear map was proposed in 2003, but the first candidate proposal of such a multilinear map actually was given by Gag, Gentry, and Halevi in 2013. It's actually a modification of, at least the way I look at it, it's a modification of the entry-based fully homomorphic encryption scheme. And entry is a lattice assumption, so it somehow falls into the lattice category. It actually gives it a new way to think about multilinear maps, which you can think about multilinear maps as homomorphic encryption plus public zero text. In other words, so suppose you have a homomorphic encryption and you have the ability to test whether you are encrypting 0 versus encrypting non-zero elements, then this gives a multilinear map lag object. So although it's a little bit confusing, maybe if you're thinking about homomorphic for bit encryption, right, your encryption 0 or 1, then actually if you're allowed to publicly test 0 or 1, you somehow lose all the security. So I should add that you should think about it as you're given a homomorphic encryption scheme, but you're only allowed to test whether it's a 0 value or a non-zero value in some constraint. For example, after you do the order evaluation, you can test. And think about it, it's encoding not 0, 1, but it's a really exponential size domain. That's easy to think about. So I think it's fair to say that following the initial approach of GG13, there are two other proposals for lattice-based multilinear maps by Kong et al. And the other one, which is GG15, which will be the focus of the talk today. So both of these two multilinear maps, starting from modifying some previous existing homomorphic encryption scheme. So like this CLT13 is based on FHE scheme from like an approximate GCD problem, which is also sort of a lattice problem because the best attack is a lattice attack. And the GGH15 is from another way of viewing the GSW FHE, for which Hotep has talked about yesterday. So before jumping to how the multilinear maps look like, let me give a brief overview of what's the application of multilinear map nowadays. So this is a partial picture of like what is implied by multilinear map if it is secure. So I think among this map, this is another map. The most famous application from multilinear map is arguably indistinguishability obfuscation, also constructed in the same year of the GG13 paper. So what is indistinguishability obfuscation? So, the definition was proposed like also in the beginning of the 21st century. So an obfuscator is a compiler that takes a program, say here is F, and output an obfuscated code of F. So we say an obfuscator satisfies indistinguishability obfuscation if you start from two programs which has the identical functionality. Maybe their functionality is equivalent, but maybe their details are totally different. But after you obfuscate them, they are totally indistinguishable from a polynomial time adversary. So if there's such an obfuscator, we call it indistinguishability obfuscation. So during the past, like right now it's already 6 years from the first candidate I/O, there has been many like construction proposals and many attacks from about I/O. So the current status is still there's no like indistinguishability obfuscation from standard assumptions like LWE, or even like what Chris talked about in the morning, like even crazy assumptions about LWE, there's no construction. And I think so. This kind of citation list is actually like so as you can see the construction. I stop at the 16th. If you continue, you can put the whole screen of the new proposals. And the cryptanalysis, I also stop at 18. If you continue, there's more proposals. So still, like candidates, the number of candidates are growing more than the number of attacks. So you can assume right now there are some I/O schemes which exist because we don't have the time to attack them all. So all right. So what's the landscape of the whole implication of multilinear maps and obfuscation and all the applications? So unlike for the homomorphic encryption, for which at least we know two major candidates, so two major constructions, which we know they are as secure as LWE. For multilinear maps, we should think about multilinear maps really as an abstraction or as a framework. So you use multilinear maps to build other applications. But there's no guarantee for, so there's functionality guarantee for the applications built from multilinear map. But the multilinear map itself hasn't been based on like a standard assumption like LWE. In fact, all the attacks in the previous page, you can think about them as attacks on the multilinear maps itself. So here's the current status of, at least the partial current status of the multilinear map applications. So for some applications built from multilinear maps, for example, some special obfuscation called lockable obfuscation, or some pseudo-random functions for the private constrained pseudo-random functions. So these two applications, if you follow the multilinear map framework, after you generalize it, after you work really hard, you can show they are as secure as the standard learning with errors problems. So however, the other applications are not clear. So for multi-party key agreement, I think almost all broken, except very few very complicated candidates, which is almost as complicated as I/O itself. And I/O, some of them are broken, some of them are not broken. I put an extra dose from there because right now there's also a proposal from, many proposals from building I/O from trilinear, like low-degree linear maps, plus functional encryptions, which are because they give up using multilinear maps directly. And somehow in between includes something called a witness encryption, which is I will also try to talk about today. So we have a candidate, we don't know how to base the security on LWE, also there's no attack known. So roughly speaking, all the applications falls into these three categories. Of course, these three categories are almost complete, so anything can do these three. This is the landscape of multilinear maps. So in some sense, a summary of the introduction part is, multilinear map, I'm going to talk about the construction today, and its security analysis depends on what's the application you're building from it. So right now we have some secure applications. We have some applications, if you can prove it's secure or break it, it will be very interesting. So this is the rough feeling about the multilinear maps from lattices, and we'll see what happens in the next 1.5 hours. All right. So I finished the introduction of multilinear maps and its landscapes. The focus of today will be talking about the GGH15 multilinear maps, because that's the source of applications where you can base on learning with errors. So I will first go over the basic GGH15 construction without using any applications, just describing the framework. And I will give a brief overview of its functionality and security. And then in part 3, I will explain applications. I will explain two applications which are like private constraint PRF and witness encryption. I will not mention obfuscation because just to describe the functionality maybe take 1 hour. I tried before, I gave up now. So I'll only mention maybe 2 more slides about obfuscation later. And as I mentioned before, I will mention open problems throughout the talk. And I will prepare some bonus that covers the interesting missing topics in the previous talks. So any questions so far? Right, I guess there's not many questions because I haven't touched anything concrete yet. All right, so let's go to concrete stuff from now. All right. So still, quick recall of learning with errors. So if you come to the lattice workshop for 2 days, at least you should learn about the learning with errors problem briefly. So let me record this problem again. So for this talk, it's easy to think about, it's convenient to think about learning with errors as I gave you a public matrix A, and I gave you a few LW samples, which I denoted as Y. So Y equals to a secret times a public matrix A plus a small noise. So the search LW asks that give the public matrix A and the LW sample Y, ask you to find the S. Or actually, if you find the errors, you can also just delete the error and then find the S by linear algebra. So the decisional LWE says give you A, try to distinguish Y from random. So at least when the width of the matrix is large enough, you can show that at least the distinguish this LW sample from random. It's not a trivially hard problem, because if you don't have enough sample, actually this is statistically hard, because the real and the random case are both close to random. So, previously we think about the learning with errors with one secret vector, the small s. So in this talk, it's really convenient to think about trivial generalization of learning with errors, where the secret is also a matrix. So in some sense, you are given, think about the secret as a square matrix, and you are given, like, for example, n samples, where each row is independent from each other. So you can do a quick exercise showing this is as secure as the one sample version of, one secret version of learning with error by a standard hybrid argument. And also, it's very useful to consider the Hermite normal form version of learning with errors, where the secret is from the same distribution of the error, and Applebaum et al. Shows that this is as secure as the standard LWE. All right. And okay, so after recall learning with errors, and I will not recall learning with errors. So let's have an overview of what's the high-level idea of to achieve such a capability using lattices constructions. So recall the goal is to mimic what happened in the group, where you're given a lot of like discrete log samples, like a g to the s1, g to the s2, or blah. And do the multiplication over all the s in the exponent. So an analogy of like such a discrete log phenomenon can be found in lattices as follows. So you can think about the public matrix A as the generator in the discrete log group, and one LW sample, suppose the secret is a square or a single ring element. The secret can be think about as the exponent on the discrete log problem. So suppose you have a lot of such samples, maybe with the same public matrix A, maybe with different public matrix A. The problem is how to come up with the product of S times A plus E without knowing all the secrets in the clip. Right. So, all right, how to put them together. So the idea of GGH15 is actually using lattice trapdoor sampling and create more encodings to chain them together. So in some sense, you can also think about GGH15 as the blockchain in the multilinear maps, because they are trying to put more chains to connect all of them together. And so this is one of the natural way to think about it. And by the way, I would like to also mention that this idea of chaining LW sample also appeared in the work of Kupula and Waters and Alamati and Pikert in 2016. So I think it's also fair to attribute them of like independently propose the same idea. But the applications in these two works are like showing circular security, showing counterexample for circular security for public encryption schemes. So that's why they receive less attention, because the application is too involved. But throughout this talk, I will still call such idea GGH15, because that gives a more systematic way of viewing such a construction. All right. So. Alright, so this is the idea. So now I'm going to jump into lattice trapdoors and explain how to use trapdoor to chain them together. But before I explain how to chain them together, let me actually recall lattice trapdoor, or maybe let's call it a reintroduced lattice trapdoor, because it's a very interesting concept and is very important in lattice-based cryptography. So the trapdoor of a public matrix A, we can think about its functionality as you can solve SIS problem with respect to that public matrix, or solve LW problem with respect to such a public matrix. So, formally, so what does it mean by solve SIS or ISIS? So you are given the public matrix A, and then you are given the target image Y. So you are supposed to find a short pre-image of Y. So we know without the trapdoor, if I give you a random matrix A and any target, it's hard to find such a short pre-image. But if you have a trapdoor for the public matrix A, then you can find such a short pre-image efficiently. So let me first give you the first construction of the lattice trapdoor, which is given by ITI99. So this is a classical paper. Okay, let me jump to it. Let me skip this part. So if you have a 4-rank matrix, which is 4-rank in the integer ring, not mod ZQ, that satisfies the following relation, that A times T equals to 0. So note that T is 4-rank in Z. Actually, it's a quick reminder showing that you can show that T cannot be 4-rank in ZQ, because as the kernel of some non-trivial matrix A, you cannot be 4-rank by yourself over ZQ. But it turns out you can build it over a 4-rank over Z. So what ITI shows is like any such matrix, which is short and 4-rank in Z, you can use this as a lattice trapdoor. So you can use this as the trapdoor for A. So let me give you a brief example of at least showing you how to use such a T to solve LW problem given such a T. So suppose you're given a matrix A and the Y equals to SA plus E as the LW sample. So what you can do is you can compute Y times T mod Q, and you get SA plus E times T. So SAT equals to S0, because A times T equals to 0. So this part cancels out, so you're only left with error times T. So now, so by the way, you do all of this mod Q, and then you can notice that E times T, the result of E times T is actually small, even mod Q, in the sense that everything is very close to 0 in ZQ. So you take this value directly, interpret it as a value over the integer, then the error can be exactly recovered by multiplying T inverse, which is the T inverse over rational, on the right-hand side of ET. So you recover the error. After you recover the error, you can recover the secret. Any question about this? Actually, you can, another way to digest it is you can show that, so something which is very important is you get the value over integer, but not mod Q, because even if you do mod Q, do T inverse, you won't get anything. So maybe that is about offline. All right, so this is the bonus slides from a question from yesterday about how to generate a trapdoor given, how to generate A together with a trapdoor. So this is to date, this is the most simple way of generating a lattice trapdoor, generating a matrix A with a trapdoor. So recall the gadget matrix that Hotak talked about yesterday, and it's also talked about today. So the gadget matrix is very structured. So think about B is a small integer like 2. So you're given 1, 2, 4, 8, blah, 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 all the way to 2 to the k minus 1 in the first row. Then shift in the second row, then all the way to the last row. Another way to write it is to write it as identity matrix tensoring this gadget vector 1, 2, 4, 4, 8, 16. So it turns out that for this gadget lattice, it has an easily computable shorter basis on the right. And maybe saying in other words, is solving SIS problem for this public matrix is super easy. So how do you do this? So given any integer, you can solve the shorted SIS problem with respect to this public matrix by simply do the binary decomposition of the number and put it into the columns. And you do a routing calculation, you can show that the vector times the column vector equals to the original number since you're doing a bit decomposition, every bit is a bit, it is small, so it's great. So after you have this public gadget, so you can construct a matrix A with such a trapdoor as follows. So first sample a random matrix A prime with proper dimension, and then put it together with G minus this random matrix A prime, then put it together with G minus A prime times a small matrix R. So as you can see, this matrix A times R over I as a column matrix, this recovers the gadget matrix. So so how to solve SIS given the R and I? So you can first solve SIS problem with the gadget matrix G, as I told you in the previous slide, and then multiply on the left by R times I. This gives a Schrödinger solution for the target over the previous matrix A. So this at least gives you a way to find the arbitrary preimage. Although a simple preimage from a complicated distribution is another story, which I won't discuss in details today, but at least it could give you a brief flavor of how to generate a trapdoor, and at least how to use the trapdoor to sample preimage from not very specific distribution. All right. So instead of telling the details of all the complicated sampling procedure, let me mention a property that I'm going to need in the rest of the talk, which is sampling a preimage from a distribution without revealing the trapdoor. So this is proved in the work of Gentry, Pikett, Vaikutanasa. So think about in the real world that you are supposed to find the preimage of a random target. So it's very important it's a random target. So here it means like you're given a public matrix A and the random target U, and you use the trapdoor to sample the preimage of U and the A, which we denote as D, and such that A times D equals to U. GPV proposes an efficient algorithm of sampling D from a distribution which has the following property. So in the real world, you sample D with a trapdoor, but you can actually produce the same distribution, not the same distribution, it's a statistically close distribution in another way. So since I'm coming from electrical engineering background, I will use this notation to denote whatever things without sampling without a trapdoor. So it turns out you can simulate the previous distribution as follows. So you sample a matrix with the same dimension without using trapdoor, and then you also sample a short vector from a specific distribution without using the trapdoor of A, because there's no trapdoor of A, and you produce D, a U, by multiplying A and D. So actually you can reproduce A, D, U from the distribution that is statistically close to a distribution from the trapdoor generation. So this is a very important lemma that we are going to use in the analysis of multilinear maps. So let me give you more flavor of why it's important that U is from random. So suppose U is from 0 in the other how to say extreme side. Then actually, if you sample a preimage of 0, as I defined for the lattice trapdoor by I type, actually some preimage of 0 already constitute to the trapdoor of A. So in some sense, if you are required to sample the preimage of 0 for sufficient amount of zeros, then you already recover a full functional trapdoor for A. So in some sense, proving this theorem for arbitrary image is impossible, but there's some middle ground which is also interesting. What we can prove now is that if the target U is from uniform, then we have such a lemma. It's kind of another way to think about it is you can pretend you're not using a trapdoor in analysis. Any questions so far? All right. Alright, so after introducing the trapdoor, I can give you the GGH15 in a nutshell. So in a nutshell, meaning that I will give you a very small example. So the small example consists of only 2 multiplications. In some sense, let's see at least how to use this idea to reproduce by linear map. So suppose I have 2 LW samples, S1A1 plus E1 and S2A2 plus E2, that I want to jump to a result of S1 times S2 times A2 plus E without revealing S1 and S2. So the idea of GGH15 is the following. So suppose I already have the trapdoor of A1 and A0, and the most important part is, A1 is used to sample the preimage of the next one, and it's also used as the public matrix of the previous one. So A1 is really the connecting point here. So if I use the trapdoor of AI minus 1 to sample, the encoding of DI for the corresponding LWE sample in the front, so pictorially it looks as follows. So I have the D1 think about D1 as the encoding of S1 and the D2 as the encoding of S2. So if I have these encodings, so let me jump to the next slide first. So if I have these 2 encoding, D1 and D2, as the encodings of S1 and S2, what I can do is evaluate as following. I compute A times D1 times D2, and then let's look carefully how this evaluation goes. So you have first compute A0 times D1. It opens to the first LW sample, S1, A1, E1, and now we multiply by D2. So we put D2 inside. We will have the first component being S1, A1, D2. So A1, D2 opens to S2 times A2. And this is the functionality part of what we care about. And since we choose the secret S as small, and D is also small by the property of the trapdoor sampling, and errors are small, by design, so the rest of the elements are all small, in the remainder. So this provides the functionality of what we are thinking about, at least, just to produce S1, S2 times A without revealing S1 and S2 in the middle. And if we look at the previous slides, so this is the most important picture if you want to remember something about GGH15. And you can see it's actually very close to what Hotak described yesterday about the eigenvector point of view. So think about the encoding of S1 is a matrix, is a small matrix whose eigenvalue is S1. So although, normally we think about it as a matrix, but it's sort of in the same position. And the eigenvectors here, they are not equal, but because we want to chain them together, but you can sort of similar. So that's why you can imagine how the GGH15 authors, they generalize the GSW FHE encryption scheme because the similarity here. And also you plus some noise for the LW to work through for some analysis. And this is the rough picture, the rough intuition of how GGH15 is obtained from another angle. Alright? So let me give you another toy example of the GGH15 piece. Alright, so the question is, do you have the security issue of using the same A? So this turns out to be a great question. But to answer that, I guess we need to go through the security analysis, because right now I haven't talked about security. The hope is the encoding of D1 and D2 does not reveal S, but we haven't proved anything yet. And you can also use the same A across the level to achieve the same functionality. It turns out that if you reuse A, it's even easier to break the scheme if I jump to the result. But it's a very interesting problem to understand because in some circumstance, we do need them to have the same A to perform even the functionality. And I think it's a very interesting problem to identify in which case they are secure or not. So in general, identifying in which case they are secure or not is a big open problem in the study of multilinear maps. They're just very complicated. All right, so any questions before I go into the next example? All right, so let me give you another example of a typical use case of GGH15 evaluation. So sort of we are, in a lot of cases, we are using GGH15 as the, doing subset product evaluations, because the whole point of using such a construction is to do things where multiplication happen a lot. So if you want to do everything with addition, you don't really have to use multilinear maps, because you can already do additional homomorphic additive homomorphism in the basic LW schemes. So let me give you a brief example of like an evaluation of GGH15 evaluation with a longer chain. So in this example, think about all the D are still sampled by the matrix A minus 1 using the trapdoor, and it's equal to SIB times A with the next matrix plus errors. So let's understand the functionality of such a stuff again. So suppose I want to evaluate this encoding on the input 0110, and let's see how the evaluation goes. So so first you open the first A times first the D, and it opens the LW sample. And then I will take out the first ingredient as the functional ingredient, and the error, E times DDDD, as I said before, all the D are small, so small times small is small in theory. So you have the following picture. And let's continue with the next A times D. So again, you open the next level, you have some more error. So still the error times the rest of the D matrix is still small, it's relatively small. And then you go on and on and on. It gives you a subset product representation of all the secrets multiplied together, together with the last public matrix, times a relatively big error element. But just jumping to one of the phenomena you will see in GGH15, because we need to accumulate so many small elements, they're actually big. So suppose you are doing multiplication over more than constant number of steps, so you do require the modulus to be sub-exponential in order to handle so many multiplication of small elements. And so even before I continue, one of the open problems in the multilinear maps is, so whatever I talk about today, if you can come up with a more efficient and simpler construction, this will be very interesting. Because I heard some of the team have implemented the current multilinear maps. I also tried to do it in my PhD thesis. I told my advisor, let me try to implement whatever I have produced from GGH15. But even setting up the scheme for like 4 steps takes like 10 minutes on a laptop. So a very interesting open problem is just to do it simpler, and we'll see whether it's worse or not. All right. So right now I have briefly described the functionality of a multilinear map, and just to recall, the whole point is to evaluate in a test whether the product of S is 0 or not. And somehow the interesting point of designing, the technical ingredient of designing multilinear map-based application is you are trying to put in structure into the secret term. So if you think about it, if you're familiar with other like lattice-based applications, so sometimes you put the message you want to encode together with the LW sample, but the position is usually like y plus SA plus E plus B times Q over 2, so it's together with the LW sample. So I think GGH15 is one of the special case where the real point of putting the message you want to hide is to put them into the secret. Of course, in the previous example, I always assumed the secrets are purely random, so we haven't seen an example of like putting structure into the secrets yet. So right now, let me continue with an example, interesting example that puts structure into the secret terms. And again, let me mention the secret goal is to actually hide all the S given the encoding. The encoding of S is D. So in the end, we want to analyze in which case, given out this ADDDDDDD, they hide S, in which case they don't. So purely intuitively, we want to hide S, and hopefully, like all the encodings are indistinguishable from random that you can sample without using S. That will be the final way to prove it. So let's continue with the first non-trivial example of using GG15 encoding. So I will let you stare for a moment and drink some water.